Okay, I have quite the jank set up right now, but okay. So this is our graph of throwing the ball. Okay, so we're on to number 7 where we're repeating the warm-ups that we did earlier from 4 through 6 for the vertical component of the acceleration, velocity, and position. Let's see. Oh, well, we never did 6. I'll write an equation for the horizontal position as a function of time. And then graph it. Okay, so let's do 6 for the first one. So we're still on horizontal. Okay, let's graph it. Horizontal position graph. We'll label it. We have x, our distance here, and we have time. Okay, so what we knew about the velocity in the x direction graph, we did this one. Remember, it was constant. Okay, so what that tells us about this graph, the horizontal position graph, is that it's going to be linear because we're working backwards. So remember, we go from exponential to linear to constant. Okay, so remember, it's, say I have this, you know, then say this is position, we did this before, and then this would be velocity, and then that would be the acceleration, okay? But in this situation, this is the velocity, it's constant, and so that means the position is going to be linear, because say you are running at 5-minute pace, okay, the entire time on your workout. Say you go for a 2-mile run, you're running at 5-minute pace. You're going to be going a mile every 5 minutes, and you're going to increase. So say I have 5 minutes here, and then this is 10. I know that would be a little hard to see, but this is 5 minutes, 10 minutes. I'm going to be going 1 mile here, okay? Then at 10-minute pace, at 10 minutes, at 5-minute pace, I'll go 2 miles. So if you're running 5-minute pace the whole time, your velocity is constant. You're not accelerating, you're not speeding up, right? Accelerating would be going from, say I have to do a stride, right? A stride, you're accelerating, but if you're just running 5-minute pace straight, you have a constant velocity. So say this number right there would be 5-minute pace, okay? And so that would mean that that's the slope of this graph. But that is not as, that was how you'd be able to tell. But okay, so hopefully that helps you understand why this is linear, because the velocity is constant. So the horizontal position graph is going to be linear, just like this, increasing, because we're going in the positive x direction. Write an equation for the position. Okay, so this will use the second kinematic equation. So I'll say this is the equation. All right, I'm going to write, this is question 6. Okay, we have x final equals x initial, and then plus velocity initial, I believe it is, I think. It's one of the velocities, and this is all in the x direction, so I'll write x initial multiplied by t, okay? And then it's also 1/2 our acceleration in the x direction times t. Now, this would be fine, right? You could still plug in the numbers and this would all be good. You have your acceleration in your x direction, but we know that that acceleration is 0. And it's multiplied by the time squared. Sorry, that's going to be squared for the second kinematic equation. So we can just get rid of this, right? And then we can just write this. Our x final equals our x initial plus vxi times t. Which really we can leave out the x and the f because, or the I and the f, which is initial and final, because we know it's constant. So you really just have to write vx. So this would be your equation. And your constants are vx and your change in time. Okay, because remember, if our velocity is constant 5-minute pace, we're saying at 5-minute pace. This vx is always going to be 5-minute pace. Okay. Let's see, what else does it ask for? Oh, how can you determine these constants from a graph? Slope. The slope of this line is your constant velocity. So the slope of the position time graph is Vx. Okay? So in theory, say this is, we have a velocity of 5, and I'm not going to say minute pace, we'll just say that's 5 miles an hour. The slope of this linear line would therefore be 5, if this value right here is 5. Okay. Are any of these constants related to the equations for horizontal velocity or acceleration? I mean, yes. You're using the same. It's related because, one, it's derived from the second kinematic equation, but since acceleration is 0, we know that that this equation is not have acceleration in it because acceleration is 0. And we also know that it's related because we use velocity to find the position, and the velocity is constant. And knowing that helps us, find the answer. Okay. So let's go on to 7, and let's repeat 4 through 6 for vertical component. I'm going to flip, also, this is Physics Fun with Brett. Fun spelled with P-H-U-N. Okay, so we have this. I'm just going to draw this quick. You know the points and everything, like, right. Okay, that's just a bad picture of what it would be, but just for reference, that's like that. This one is this one. Okay, so 4. Looking at your sketch, how do you expect the ball's horizontal acceleration? Okay, but we're doing vertical. How would you expect the ball's vertical acceleration to change with time? Now, gravity is the same, because remember, okay, say we're going to do it like this, okay? Remember on your graph we had our vectors here, and our acceleration in vertical direction, the same the whole time. AY equals 9.8, oh, that's a G, 9.8 meters per second, which equals G, which is gravity, okay? So looking at your sketch, how do you expect the ball's vertical acceleration to change with time? It doesn't, it is constant. Write an equation giving the ball's horizontal vertical acceleration as a function of time. It can be the exact same one as you did for the x, so it would pretty much be Vy final equals Vy initial plus AY y times t. So this is as a function of time. So yeah, that would, I believe that's, I mean, you're using the first kinematic equation, and it always asks you to link it to those. Graph this equation. Okay, so let's do a graph. Do it right over here. Okay. And we're saying this is AY and this is T, okay, as a function of time right here. Okay, so our acceleration is 9.8 meters per second the whole time. And what does that mean? If it's one number the whole time, it's constant. Yes, constant. So we'll say that right there is 9.8 meters per second right there. And that means a constant graph is just a line, just like that. And it'll keep going forever, no matter what time it is. Constants, I mean, we'll say change in t is a constant for this. Sorry, I'll just write that out. Change in time, okay? And then constants is also our AY, and that's our constant, and that actually equals 9.8. As you can see, it's constant graph, flat, so it's that is constant. Now Vy and Vy final and Vy initial are not constant. Now in the x direction it is, because there's no acceleration. But now that we have a constant acceleration, these aren't going to be constant per se. Okay. How would you determine these constants from your graph? You can look at this number right here. Look at the value at which the graph is, you know, that's how you can determine it. Now number 5, we'll go into number 5 for vertical. Looking at your sketch, how do you expect the ball's vertical velocity to change with time? Is it consistent with your statements about the ball's acceleration from the previous question? Yep, so the velocity, the vertical velocity is going to decrease at a constant negative acceleration of g, or 9.8 meters per second. And remember, that's AY. Okay? Oh, I didn't even put velocity here. Sorry. Okay. Because when we get to the graph, and it is consistent with the previous question, just say yes to that. Write an equation. Okay, still recording here. Write an equation for the ball's horizontal velocity as a function of time. Well, I guess this would be the same one. Maybe there's a different equation that you could just use for this, now that I'm thinking about it. Because this would give you the velocity, but like, let's see. Because like, it just asks for, well, technically, okay, for number 4, I hope you didn't already write this, or if you did, you're writing with pencil. Technically, you don't need to have this. It would just be AY equals 9.8, and that's your equation pretty much. And so it's constant. That's pretty much all it is. Now for this one, the first kinematic equation is gonna be what you want for this equation, so that's what I wrote over there. Vy final equals Vy initial plus acceleration yt. So that's your equation, and your constants are the same as up here. It's your acceleration is constant. I mean, you know, AY and change in t are your constants. So the thing about this is why I wrote that up here is because theoretically, if I were given an initial final velocity and an initial velocity and a time, I could find the acceleration. So say at this point, I was told that the vertical velocity, this would be the initial, was 10 meters per second, positive 10 meters per second. Okay, and then I was told my final velocity is negative 10 meters per second. And I'm also told that this happened in 5 seconds. So then I could use this and it would be 10, or like, oh, negative 10 equals 10 plus AY multiplied by 5. Okay, so you could find the acceleration if you're given a final velocity, initial velocity, and a time. Now, let's draw the graph for this. Okay, let's believe what it asks. Yeah, it says graph this equation. If we're going from a constant flat graph, and we're going backwards from acceleration to velocity, that means our graph is going to be linear. Similar to how on this side, our velocity was flat, and we worked backwards to position, it's going to be linear. Now, in this situation, the acceleration is constant, so that means our velocity is going to be linear. But it's going to look, and we talked about this a little bit, you got it. We're starting positive, right? So this was big, this was smaller, 0, and then this was here, and then it got even bigger down here. So that means it's going to start bigger, okay? Start positive, but it's decreasing. Okay, this is negative, well, this really should be negative 9.8, I'm sorry. You know what I mean. And this would technically be down below the graph here. Okay, so that's kind of my bad. Hopefully I don't confuse you. Negative 9.8. Okay, negative. You know, gravity works down, so it's negative. So this would technically, if I redrew this graph, this one here, I would draw it like this. Say I'm like this, and I have like that. There. That would be your negative 9.8 right there. Okay, so then we're going here and down, okay? So this is what our graph would look like for velocity. So, and this point here, okay, is Vy equals 0. That is this point up here. Vy equals 0, okay? Because we know that it's flat right here. And so then our velocity is going to be 0 because, like I said earlier, it's the point where it's going up, and then it's that point right there where it's not going up yet, or it's not going up anymore, but it's not going down at all. So then it goes down. So we start throwing the ball up, right? It's positive, but it's slowing down as it goes up because gravity is always acting on it, okay? And then it passes this point, and then that's there, and then we can start to see it's going down. So this part right here, when it gets below the x-axis, it's going down. It is heading down. Anywhere below, the ball is going down. It's going down, okay? Here it's going up, but it's slowly starting to go up less and less and less, and then it goes down, and it speeds up on its way down. How would you determine these constants from the graph? This slope right here, you see this is a negative slope, and I'm sorry if this is confusing because I wrote this as a positive 9.8, but you can see that oh, this is a negative 9.8. And so it has to be a negative slope, and that's why this is here. So this slope of this equals our acceleration in the y direction, negative 9.8. That's the slope. Okay, I think that's about it for 5, so we can go on to 6 here. Write an equation for the ball's horizontal position as a function of time. Okay, horizontal position as a function of time. Second kinematic equation here, okay? We have we'll just say y final equals y initial plus vy times t plus 1/2 ayt squared. Now remember, in this side, we use that same equation for the x direction, okay? The horizontal direction. But in this situation, our acceleration was 0, so we could just cross that out. But in this equation for vertical, our acceleration is not 0, so we have to leave it at this for your equation. And our constants are still the same, change in t and ay. You know, constants all the way through. That does not look like constants, but you know, you get it. Okay? How would you determine these constants from your graph? Oh, I haven't drawn a graph. Gotta graph it. Okay, let's put the graph right here. Right here. Let's see, how do I want to do this? Oh. Well, we already did this, technically. Kind of. It's going to look similar to this one. Okay, so oh, wait a minute. How do I want to do this? Let me think for a second here. Sorry. What is this one going to look like? Okay, so I'm thinking we have negative velocity going through, and it's going, so I'll just say, I mean, we know that it's going to be like an exponential decrease, okay? But with that said, we're never going backwards, okay? So our position time for this is always going to stay above the x-axis, right? Oh, wait a minute. No, it's literally not. Great job, Brett. So we're starting at this height, okay? You know what? I'm going to just re-explain this on a different piece of paper. Give me a sec here. I'll draw this one. This is the main one again, okay? Remember, we start down here, we go, ooh, okay? So, we start at this height, okay? Vertical position. We start at that point, and we go up a little bit, and then we go down. Okay, so the graph for our vertical position, our y position, we're starting at this positive point, right? So this is t, and this is y, okay? Y position. We start, so you could do this two ways, technically. You could say this is 0. Well, this is where it gets kind of technical. You could say this is 0, or you could say this is 0. You know, we're going to go with that 0. So then it's just going to be like, you know, the same graph, actually. Is it? Okay, hang on here. Am I done? Because I think it's going to be the same graph, right? So our position, we go up more, and then we decrease. But it's leveling off. Yeah, so it's literally just going to be this. It's the same as this. And I know it can be confusing. Don't worry about it too much, that it's the same. The reason that it's the same is because in this main one, in this one, our horizontal velocity is constant, so it doesn't like affect the shape of the graph. So that's why, you know, this looks that way. But we know it's not exponentially increasing, it's decreasing, right? So our velocity slope looked like this, right? Looked like that, okay? This point is this point, okay? Because we're at 0. All right, our velocity is at 0, and we can tell our position is not increasing or decreasing right here, right? So our velocity is 0 when the ball is tossed up. Ball is tossed up in the air, and it's right at this moment before it starts to head down. It's at 0, like I said before, and so our position isn't changing. So that's why this right here is flat at that point. That is where this is, okay? Because this velocity 0, that means the slope is 0 right here at that point. That's why it's flat there. And then it starts to head down. And at this point, if it's starting to head down, that's this. So from here to here, okay, from point A to point B on this graph, that's point A here to point B here. It's kind of confusing to explain. It's easier if you ask me questions on what you were confused, because that's probably the most confusing part, because I can see I can be confused how, like, what? Why are these the same? But yeah, so that's what the graph looks like for the YT here. And then let's get, how would you determine these constants from your graph? You couldn't. Just say it would be too difficult to determine them from the graph. And then they're related. It literally just asks, for number 6, are these constants related to the equations for horizontal velocity and acceleration? And you can just say, yes, it's related to both horizontal velocity and acceleration equations. Just say yes. It doesn't ask for why. So yes, there you go. Let's move on to the prediction. Oh shoot, my computer's tweaking here. Okay. Make a rough sketch of how you expect the horizontal velocity versus time to look, a graph of the horizontal velocity versus time to look for the thrown object. Didn't we do that? Or like, am I done? We literally did that. So your prediction is, just like we did over on this side, horizontal, wait, is it vertical? Horizontal. Horizontal velocity versus time is this, right here. We already did it, okay? So it's that. That's what we expect it to look like. And then when it asks, do you think the horizontal component of the object's velocity changes during its flight? We say no, because it has no acceleration. It has a constant velocity. For the prediction part, so we're doing the prediction here. We got this. Bang. Does not change. And that is because y equals 0, so v, or we're doing horizontal, sorry. Acceleration in the x direction 0, so that means the velocity is constant. Okay, So the horizontal component does not change. That's what it asks for. Horizontal component does not change. Okay. Sorry, super messy handwriting because I'm doing it fast. Or do you think it is constant? Oh, yeah, it's constant. Explain your reasoning. All you have to say is it is constant because the acceleration is 0. It's constant because of that. Okay? It's a little circle of life right here. The acceleration is 0. That means the velocity is constant. If the velocity is constant, acceleration 0. Okay? So when you explain that question for your prediction, you can just say it is constant because the acceleration of the horizontal velocity is 0. I'll write it out for you. That's all you need. 2, make a rough sketch of how you expect to graph the vertical velocity every time to look for the object. We also did this. You remember what this one looks like? Bang. Just like that. Okay? That's VYT. Do you think the vertical component of the object velocity changes during its flight? It does change. And remember, because we do have an acceleration, okay? We have an acceleration, it's negative 9.8. It is g, right? That's g. Okay, this is time. It's a little confusing, so, right? So you could say, to answer this question, the vertical component of the velocity. Thank goodness it's still recording. This is kind of turning into a long video. Sorry about that. I'm just trying to thoroughly explain it. The vertical component of the velocity changes as a result of the constant vertical acceleration of negative 9.8 meters per second, or gravity, g. That's all you need to say. So yes, it will change. It starts positive and then goes negative. Starts positive, goes negative because of this. Right here, that negative 9.8, it looks nothing like negative 8. Okay, that's all I have for today. Hope that was helpful, you can understand it. This is kind of a long video, so I apologize for that. If you have any more questions, feel free to text me. 952-242-6654. Or email me at bce35869@bethel.edu. Yep. Actually, I forgot to sign my work here. Doctor. Yeah, I'm a doctor, that's right. Dr. Elias.